Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the different variables that influence the rate at which rocks will chemically weather. Let's begin our discussion with a look at two tombstones found in the same cemetery. The tombstone on the left was erected in 1868, the tombstone on the right, 1872. The one on the right is younger by a good 4 years. However, you can see that the one on the right does not look very good. It's not standing the test of time very well. Whereas the one on the left is standing the test of time pretty darn well indeed. You can still read the inscription and everything. So what's the difference here? Well, the one on the left is made of granite, a rock that's dominated by quartz and potassium feldspar and some plagioclase feldspar too. So basically that's made out of minerals that are either stable or metastable in the environment of Earth's surface. In contrast, the example on the right is made of marble. Marble, of course, is dominated by the mineral calcite, and calcite is not only much softer than quartz or feldspar, but it is also chemically more susceptible to being dissolved away by weakly acidic rainwater. So the material that a tombstone is made from ends up mattering, and this is a good lesson for understanding the rate at which rocks weather. Composition matters. Here's a look at some of the results of different compositions weathering under the same conditions. This is shiprock in New Mexico. We've looked at shiprock in another Smart Figure. You can see the central volcanic neck here that used to be at the heart of a composite volcano. And then there's a very prominent dike where igneous rock has filled in a crack in the surrounding rock. There's another dike over there. And those igneous rocks are basically standing up tougher to weathering than the surrounding sedimentary rocks they cut across. So all the rock around them is weathering away at a faster rate, and as a result, the igneous rock pokes out of the landscape because it's weathering away more slowly. That's called differential weathering. Another example of differential weathering can be found in the Appalachian Mountains of the eastern United States. We're looking here at the Valley and Ridge Province, in this case in Pennsylvania, where actually they call it the Ridge and Valley Province. But you can see here that we've got alternating ridges and valleys. Ridges and valleys. And so the reason we've got ridges and valleys there is that the ridges are held up by very quartz-rich sedimentary layers, sandstones and conglomerates, whereas the valleys are underlain by shales and limestones, rather weak layers that don't stand up as well to weathering. So that's another nice example of differential weathering. Another variable to consider is climate. You're looking here at a gully eroded into laterite. Laterite is a bright red tropical soil. Warmer, wetter climates tend to produce faster rates of weathering than cooler or drier climates. So the water helps facilitate all kinds of chemical reactions, dissolution, hydrolysis, and oxidation. And then the temperature, of course, provides the energy to run those reactions. So higher temperatures have more heat energy, and the opposite, of course, would be true in a colder environment. So one of the review questions at the end of the chapter basically asks you to imagine a block of granite looking like the one on the left there, and then imagine that granite going into two different scenarios. One is we take that block of granite and we stick it in one of the dry valleys of Antarctica, or we can stick it in a jungle in some place like Costa Rica. So let's first consider the scenario where we put it in this dry valley of Antarctica. What do you think is going to happen to it there? Okay, hopefully your answer is not much. Basically, because that is a very cold environment and a very dry environment, it is called the dry valleys after all. There's not a whole lot of precipitation there. You are not going to expect much to happen to that granite. It's going to have a very slow rate of weathering. In fact, some of these blocks of granite here may have been there for millions of years. On the other hand, if we put that same block of granite in very different climatic conditions, such as in a warm, wet climate like the one pictured below, we would expect it to rot pretty quickly, to fall apart. So the ferromagnesian minerals are going to end up oxidizing. The feldspars are going to end up undergoing hydrolysis and producing clays. And then as the rock loses its structural integrity, physical weathering will take over and it'll be broken up into smaller and smaller pieces. Thanks very much for your attention. This concludes yet another Smart Figure.